hand over to Martin if you want to share your screen.
Thank you. Does that look okay for you?
Yep, I can see that fine.
Okay, thanks for the introduction. Well, thanks for having me at this meeting. I'd like to hear more from you as well. And thinking about the topic, I think that one of the first things that came to mind, living in the Netherlands, is our 1953 storm, which was the last storm that we had where there was any coastal flooding. And this is a very old picture from that. And that's just as an inspiration for some of the work that I'd like to show today. The topic will be on global modeling of tide storm surges, extreme sea levels, and some of the flood events, and focusing on GTSM. While preparing this talk, I was actually looking outside, and it's a bit stormy over here. And there's a bit of an autumn storm going on, and I've here also put a picture up of the weather forecast for tomorrow. And you can see on the left some precipitation, and on the right the wind field. Now these winds, they're of course pushing the seawater towards the coast, and that will give an increase, lead to an increase of sea level. And that's what this talk will be all about. If we look at the national system that we have available here in the Netherlands, take a particular location. This is Hoek van Holland. Doesn't matter really. That is where the red pointer is on the map. You can see that the blue line is giving the forecast for tomorrow, and you can see that the water level, which goes up and down with tides, tomorrow will rise above the normal level up to about 220 or so, which is sufficient to sort of to keep some of the services on alert, but nothing serious. For example, the storm surge barrier that is there at Hoek of Holland will close at about 3 meters, so this is nowhere near. I just wanted to use this as an introduction because a lot of this stuff is working on a national level. It's organized by national governments here in Europe, and I guess in many places around the world. But for some studies, it's also useful to look at this at a global perspective, and that's true for, I think, for 2 reasons. One is that helps us compare between different regions with a uniform approach, and the second is that there are some regions in the world that are not. There are a lot of forecasting systems, but they don't cover everywhere. So a long time ago, we started on a storm surge model, which I will tell a lot about. And if we look at that model, it's built into an operational environment. I know that's not the talk of today, but I can use that to show a bit of the dynamics. You can see the tides moving around our planet. And if we then my bad. Yeah, if we then zoom in again to Hoek of Holland, you can see that we can make a somewhat similar forecast using a global model. Yeah, if you remember from the previous picture, this is rather similar. I also want to use this picture to highlight that you can clearly see that the high water level is formed by a combination of spring tides and a storm pushing the water to the coast at the same time. We can also, what we often do is compute tides, which is then the regular predictable part of the pattern, and subtract that from the total water level, which gives us what we call surge. That's this wiggly pattern over here. To a large extent, that's the effect that you see from the wind, and but it also contains some interaction between the tide and its surge parts. So you can see the variations over time. Those are caused by the nonlinear interactions. So this is the system that we've got up and running. More about that. Also wanted to mention that this data is also available to you. If you go to blueearthdata.org after the meeting or so, you can have a look and see the same data as I'm showing you here in the slides. For today, I'd like to talk about 3 topics. One is something about the model and its developments. 2 is about reanalysis and climate projections. And 3 is about flood maps. So talking about the model. This model that we're using is an unstructured grid model. That's why there's large cells over the ocean and much smaller cells close to the coast. That gives us an efficient distribution of the computational power to be used where it's needed and be faster where it's not. It's a barotropic 2D model, which makes it relatively fast. And we also have an option to force with external sources of sea level rise, so we can input a sea level rise scenario to look at the future weather, future scenarios. The tides in this model, contrary to some of the regional models, is not driven by boundary conditions, but by the tidal potential. So the gravity field from the sun and the moon, etc., is directly modeled into this system and is driving the tides. The search is, of course, driven with the air pressure and wind fields from an external meteorological model, which is sometimes, you'll see some sources during this talk. What is also important to model at this scale is the tides at the larger scales also affect gravity of the planet itself, and you have to account for this feedback in the modeling. Because we're using a 2D model, we have to account for some of the aspects of stratification in the ocean, which are known as internal tides. So we have a parameterization for that. That I think, in short, gives you an overview of what this model is and can do. It's been developed over time. From an earlier prototype in 2011, we had the first real version, I think, in 2013. And you can see here over time, it's not about the details, this picture. I just wanted to show you that version by version, we keep on improving things. And there's a number of trends in there. You can see that there's roughly an increase in resolution from top to bottom. And so especially the coastal resolution is increasing. If you look at the errors of the model compared to the different data sets, you can also see that they are decreasing over time, which means that we're creating a more and more accurate model over time. And it's still actively ongoing. So this version 5 is not there. It's work in progress. Version 4.1 has just been completed, and some of the work shown in this talk will be about version 3, and some will be about 4.1. To give you some idea of the kind of developments that are ongoing, for us, bathymetry is very important. We're currently using a combination of JEPCO, AMAPNet, and several other sources. And those have to be updated over time, not so much because the bathymetry is changing, but our understanding and the quality of the data sets are improving over time. So we keep on updating those. What we recently did is we added a lot more tidal constituents to the tidal potential, so made the forcing for the tides more accurate. We updated the fields for the internal tide parameterization, improved numerics, reduced memory consumption, and we spent a lot of effort on calibration of the model. And I have 2 more slides about this calibration. Perhaps I should. No, it's okay. Calibration. 2 of the parameters that we're using, which is the bathymetry and friction parameters, those are not very well and not accurately known. So what we need to make a model of the accuracy that we currently have is to calibrate this. We do this by defining a cost function of a misfit between the model outputs and available measurements. And what we tune is bathymetry. What you can see here on the lower left are adjustments to the bathymetry during the calibration, and that's a fraction. And so we just adjust by a few percent. And well, something like 0.02 means 2% deeper. And on the right, you see adjustments to friction, especially in the shallow areas with large tides. There's That's where most of the friction is happening. There's about 3 terawatts or so being dissipated continuously, and much of that is in these marked regions. You can see that during the calibration, the cost function sort of reduces by a factor of 4 or so, which corresponds to an increase in accuracy of a factor 2, because we have a quadratic criterion, and we'll see that in a second. If you want to read more about that, there's a paper. There are more papers coming up, but they're not done yet. To give you an idea about the accuracy, this is probably too small to look at all of the details, but what you can see, just to look at a few numbers, if we compare to FES, which is one of the most accurate tidal models in deep water, you can see that before calibration, we had an accuracy of about 5 centimeters in deep water, and after calibration, that's about 2.5, you see? So that's a pretty good reduction. Then if we look at coastal stations, that's the University of Hawaii Sea Level, UHSLC dataset, you can see that there's also a good improvement, but a bit less. That's because at the coast, a lot more things play a role, and it's there's a lot more work needs to go in there. But so most of the improvement starts from deep water, and now we're slowly moving towards the shallower water. And still, the model is reasonably competitive, I think, with a regional tide model, a tide surge model. You can see also spatially here at the top, on the top left, you see here an idea of the accuracy of the model that's in meters. Typically it's a few centimeters in deep water, corresponding to the other one. And on the right, you see the difference before and after calibration, where all of the positive numbers are improvements. So you see that roughly in most of the places, we're moving forward by calibration. There's a bunch of other data sets that we're also comparing to, because there's a lot of details about this that I don't have time to go into today. Moving forward towards the future versions, again, more updating of data sets, further improvement of parameterizations, changes to numerics. One big step for us, I think, in the ongoing work is a new grid. We were having some problems with orthogonality of the grid. We're using a numerical method where the orthogonality does play a role. And so we started from scratch. We improved the orthogonality. We added extra refinements in places where we were seeing that it had benefit. And we also made it much more smooth. In terms of the bathymetry, we put a lot of emphasis on the Antarctic region. On the top, you see JEPCO, which means where you see that a lot of the Arctic is above sea level, Antarctic is above sea level. But if you would take away all of the glaciers there, a lot of this would be below sea level. So there's a very thick layer of ice that is actually there on top. For us, it's relevant that in a lot of places, especially here in the Weddell Sea, there's a thick layer of ice, but then beneath that, there's water before you reach the seabed. And that's important to take into account in our modeling. So we spend some effort over there. Looking at the grid, you can see resolutions on the left, and is the 4.1 version, and on the right 5. What you can see here that it's much more smooth than it was. There's a bit higher resolution, and you can also see that we have most of the resolution near the coast, and also in some places where there is steep topography. That's the typical places where we put the emphasis. One small topic that we have got ongoing, which is related to climate change, is to better model the effects of the Arctic sea ice. We're looking into remote sensing data to better estimate the influence of sea ice on tides and storm surges. And the picture on the right shows some work with the buoy data set. But the final aim of this is to improve our parameterizations for effects of sea ice on tides and storm surges. So having this model, already quite a while ago, we started looking at reanalysis and climate projections. And this work all started with the PhD of Sanne Muis, who before 2016 looked at the ERA interim reanalysis. So she ran the model, the GTSM model at that time, with forcing from 1979 until I think 2016 or so, and computed extreme sea level statistics for that. So what you see here, for example, on this map is a return 10-year return period. You can see the water levels that correspond to that. To give you some idea, we picked some random points in space, and you can see the larger storms, both available as they are available in the observations in blue and as they are available in the model in red, and the fits of the extreme value statistics. Yeah, these are annual maxima. After that time, of course, better models became available. So we updated, also we looked at the model performance of, in this case, version 3, which was much improved over the previous version. On the left, you see, for example, some time series around Hurricane Sandy. And you can see that there's a pretty good fit between observations and model for the various locations around New York. You can also look at the statistics on the right, which gives you RMS errors for the search. If you want to read more about this, there's a lot of detail in this paper by Marjan. So it gave us confidence that we could do better than initially, and there's actually a lot more things to be said for which I don't have time, which led to an update of this data set for the Copernicus climate services. That so these time series for the whole of the ERA period are available in there in terms of reanalysis. So you can just download time series, but there's also statistics. It's available for Europe, more or less the picture that you're seeing out there. But there's also some information on climate change. So there was a model run with a climate model. It was a KNMI model together with Danish Meteorological Institute, looking at the future statistics and how they compare to the present day statistics. These are mainly shown to introduce some of the recent work, because recently my colleagues have, with various other institutes, together with various other institutes, they produced an updated data set, and it's improved in various ways. So first of all, they moved for the climate model from the CMIP5 model that was being used at that time now to a set of high-res CMIP6 models, which have much more resolution, which is very relevant for storm surge forecasting. We updated the model, and together with these partners, they simulated a multi-model ensemble, which gives us now a much better understanding of variability between models. And it's also now global instead of European. The Copernicus Climate Service is at this time busy with putting this data online, so you should soon be able to find this on Copernicus Climate. To give you just a hint of the results, there are relatively large biases in the climate model runs between the different models. So that gives us a lot of, that's a very important outcome, I think, of this result. That is much less so for the reanalysis. So we can do a lot of work on a very accurate reanalysis, but there are much more intrinsic uncertainties in running these kind of things with the climate model. And finally, I wanted to mention a recent project we've been doing on hazard maps, flood maps. And we've been doing this together with Microsoft and their planetary computer. And what has been done is, the idea was to use create high resolution flood maps globally for current climate and some future climate, so some sea level rise scenario. We were using different topographies to get an idea of the uncertainties in those. And there was also some work on tropical cyclones, so individual storms, etc. Just to highlight some of the results in the data set itself, you can see on the right here that if you look at two DTMs, so two topographies, Merit and NASA, you can see that there are relatively large differences between the data sets, and they have an important impact on the result. There's an upcoming and recent innovation using LiDAR data, which gives us much more accuracy, but it's difficult to get the same kind of high resolution. So we've looked at 5 kilometers, 1 kilometer, but there's no higher resolution data sets available yet based on just LiDAR. The inundation modeling was relatively simple. We're using a bathtub approach with a attenuation factor. We're forcing with the GTSM data, like earlier in this talk. Model was based on ERA 5 and CMIP, so just like I was presenting in the previous section. And there were two time spans, so present day climate and future day climate based on RCP 85 scenario. That together runs in a lot, results in a lot of combinations, and all these flood maps have been computed and made available. I won't go into the details, but of course this needed to be parallelized and speed, and that was why it was useful to work together with Microsoft to speed this up and be able to do these kind of computations fast. And they're also kindly hosting the data now, so you can access all this stuff. One important finding was also that if you look from lower to higher resolution, that this affects a lot the connectivity. On the left, you see 90 meter resolution, and on the right, the 1 kilometer resolution. You see that the connectivity in this area in Mekong Delta increases a lot by having a higher resolution. So this connectivity and the resolution are very much connected. The other differences are relatively modest compared to the large differences between DTMs and the differences between resolution. Of course, there's an increase with increasing sea level rise, and there's also an increase with increasing return periods. Okay, that was my presentation. Thanks.
Wonderful.
Thanks,
Thank you. Go ahead.
Sorry. Yeah, thanks, Martin. Yeah, really interesting. I think a lot of the work that I do is looking at kind of river flooding, so it's really interesting to look at the sort of coastal boundary for us. And it's always been a problem, I guess, for us to define that well. So it's really great to see the sort of advances that you've been pioneering here, and some of the great kind of steps to improve on the models. Particularly like the sort of calibration side of it. I think that's something that's often overlooked, I think, on global scale. So that's really interesting. There's already a few questions for you in the chat, which you can kind of respond to as we go along.
Okay,
But
cool.
what I'm going to do now is hand over to the next speaker.